Good morning students, myself Dr. J.P. Sridhar, Associate Professor, Department of Electrical Engineering, SJBIT. I welcome you all for DSP lecture videos. In this class, I am going to design the low pass Butterworth filter. What are the steps to be followed for design of the low pass Butterworth filter? Let us start the class. As we already last class we discussed how to find the order and cutoff frequency of the low pass Butterworth filter. Here once you know the given specifications, so what are the steps to be followed for designing any Butterworth filter? So in exam they will give the question, so that question contains the 4 parameters, that is gain and frequency parameters. You should know Kp is nothing but pass band gain, and Ks you know that stop band gain, and H of j omega is the magnitude response of the low pass filter, and this pass band frequency and stop band frequency should be, the range is given, and this pass band frequency should be always greater than or equal to omega, and stop band frequency should be always less than or equal to omega. Okay. So whereas Kp and Ks are pass band attenuation at pass band frequency omega p in dB, and attenuation at stop band frequency omega s in dB. And once you know these specifications, you draw the magnitude squared response of the given Butterworth filter and mark all the specification. The gain should be in decibel and it is always negative, and frequency should be x axis, it should be radian per second. Frequency should be radian per second. Whenever the frequency is not in radian per second, you can sometimes they will give frequency in hertz. So that time you should convert this frequency to radian per second. In order to do that, you will get omega p analog frequency is equal to 2 pi f1 or 2 pi f2, and put that frequency, you will come to know. And whatever the value of pi is there, you can replace that pi with 3.14. So 159, you will get to know what is the analog frequency in radian per second. Once you know this, next is the order of the filter. Next one is the order of the filter n. What is the equation for order of the filter? Last class we discussed what is the value of n. So n is given by log to the base 10 of 10 to the power of minus kp by 10 minus 1 whole divided by 10 to the power of minus ks by 10 minus 1 whole divided by 2 log to the base 10 of omega p by omega s. Once you know the given specifications and all the given specifications should be in proper, then write the frequency response curve of the low pass Butterworth filter, mark all the specifications, and next step you have to calculate the order of the filter. So as I told, order of the filter, n is not an integer value, you choose the next higher integer. Suppose you will get n is equal to 2.3, you can choose n is equal to 3, n is equal to 1.2, you can take n as 2. Choose always the higher integer value when n is not an integer value, non-integer. So second step is, once you find n, once you round off to the next higher integer value, go with the next step. Next step is to find the cutoff frequency omega c. Omega is known as cutoff frequency. Here omega c will have 2 components, that is omega c1. Omega c1 is equal to omega p divided by 10 to the power of minus kp by 10 minus 1 whole divided by 1 by 2n, whereas omega c2 is omega s divided by 10 to the power of minus ks by 10 minus 1 whole power 1 by 2n. So once you find out omega c1 and omega c2, you take the average of these two, you will get the cutoff frequency omega c. So some textbook they will take omega c as omega p or omega c as omega s also. They will follow. It is left to that, but the final answer almost remains same. So here I am following the average of the cutoff frequency omega p and omega s. So if you take omega c as omega p, that is also right, or you can consider omega c as omega s, that is also right. But I am doing here average of these two. I will get the center value, mid value, I will take that as the cutoff frequency. The next step is, once you find the order of the filter n and cutoff frequency omega c, we can go to the next step. In next step, we are finding the normalized Butterworth low pass filter. Hn of s. Normalized transfer function of the filter we are finding. What is normalized filter transfer function? Normalized transfer function of the filter is given by Hn of s. Hn of s is equal to 1 upon product of left top poles of s minus sk. This entire term is known as Bn of s. This Bn of s is known as Butterworth polynomials. Bn of s is known as Butterworth polynomials. We have to determine the Butterworth polynomial based on the value of n. Either n is an even number or n is an odd number. When n is an odd number, the procedure is different to find the Butterworth polynomials. Where n is an even number, it is also different to find the Butterworth polynomials. Now, how to find sk Butterworth polynomials? When sk is equal to 1 at an angle of pi k by n, where k should be 0, 1, 2, 3 up to 2n minus 1, when n is odd number, whereas sk is equal to 1 at an angle of pi by 2n plus pi k by n, where k is 0, 1, 2, 3 up to 2n minus 1, when n is even number. Once you do this, I will explain how to find the Butterworth polynomials in the next slide. So these are the two formulas are used to find the Butterworth polynomials sk. So once you find the Butterworth polynomial, substitute and simplify, you will get the normalized system transfer function h of n of s. That is not the actual solution. Once you know the transfer function of h n of s, we can do the analog to analog transformation, that is low pass to low pass frequency transformation, to find the desired transfer function by using the below equation. Once you know h n of s, we have to obtain h of s. This h of s is known as analog system transfer function, that is low pass to low pass frequency transformation we are using here. So h of s is equal to h n of s, where s is replaced by s by omega c. Once we already calculated omega c, that is cutoff frequency, wherever s is there, we replace s by omega c and simplify, you will get the final analog system transfer function h of s, that is the desired transfer function for the given specification in case of low pass Butterworth filter. Now let us see how to find the Butterworth polynomials sk for n is equal to even and odd number. Now I will consider n is equal to 1. When n is equal to 1 is an odd number. In odd number, what is the formula to calculate sk? Sk is equal to 1 at an angle of pi k by n, where k should be 0, 1, 2, 3 till 2n minus 1. So here n is 1, so 2 minus 1 is 1. So we will have only 2 poles, 0 and 1 here. When k is equal to 0 and 1, we have to calculate the poles now. What is sk? 1 at an angle of pi k by n. So k is 0, you will get 0 divided by anything is 0. Automatically you will get 1 at an angle 0. So angle is 0. So it is located at 0 position. Similarly, when put k is equal to 1, you will get the pole as S1. The S1 will get the angle as 180 degree. The second pole is located at 180 degree. As we know in system stability, if the poles are located at left of the S plane, then the system is called as stable system. Therefore, in Butterworth polynomial, generally what we are doing is, we are considering only the poles which are located at the left half of the S plane, and which are the poles which are located at right half of the S plane, we are neglecting. So here there are two poles, one is S0 and another one is S1. This S0 is located at right half, we are neglecting because it is positive. And one more pole S1 which is located at left half, we are considering that pole for the design and we are neglecting the S0. So therefore, in the transfer function Hn of s, here n value is 1. So H1 of s is equal to 1 divided by product of left half poles of s minus sk. So sk value is S1. So minus into minus plus, you will get s plus. What is the value of S1? So angle is pi. So here theta is 180 degree. So what is e power j theta? E power j theta is cos theta plus j sin theta. So cos 180 is minus 1. So we will get minus into minus plus 1. So S1 value is minus 1. So minus into minus plus, you will get S plus 1. You should know that how to simplify the angle in trigonometric relationship. By using trigonometric relationship, you have to simplify the angle. So similarly, when n is equal to 2, you will get 4 poles. So nh2 is an even number. In case of even number, this is the formula can be used to calculate the Butterworth polynomial Sk. So here, what is the value of k? Again, k is till 2n minus 1. So 4 minus 1 is 3. So k is equal to 0 to 3. You will get 4 poles. Out of 4 poles, one pole is at 45 degree. That is positive. We are neglecting. Second pole is at 135 degree. That is negative. Okay. Second quadrant we are considering that. And third pole is at 5 pi by 4. And fourth pole is at 7 pi by 4. Here you can observe this S0 and S3 are located right half, whereas S1 and S2 are located at left half. Out of 4 poles, we are considering only S1 and S2, and S0 and S3 are neglected because they are located at right half of the S plane. So once you know that, consider that poles S1 and S2. So you will get H2 of S is equal to 1 divided by S minus S1 and S minus S2. And what is that angle? You can calculate 3 pi by 4. You get cos 3 pi by 4 plus j sin 3 pi by 4. The value is this minus 0.707 sin 3 pi by 4. Okay, you will get minus 0.707 plus j 0.707 into S minus of minus 0.707 minus j 0.707 is S2 pole. What is S2? Cos 5 pi by 4 plus j sin pi by 4. Third quadrant, both cos and sin are negative. So both are negative value. That is the value of S2. This is the value of S1. So simplify the substitute the value of S1 and S2 and simplify. You will get S plus 0.707 minus j 0.707. So it is in the form of a minus b into a plus b. What is a minus b into a plus b? A square minus b square. So a square minus b square will be the answer. So what is a square? Is s plus 0.707 whole square. It is in the form of a plus b whole square. Simplify. So j square is minus 1. Automatically you will get 0.707 square. And you simplify, you will get h2 of s as 1 by s square plus 1.414s plus 1 as transfer function for n is equal to 2. In the same fashion, for n is equal to 3, you will get 3 poles, okay, and the rest of the 3 poles are right half poles. So S0, S1 and S5 are the poles which are at right half, whereas S2, S3 and S4 are the left half poles. So S2, S3, S4 are value can find out and substitute here S2, S3, S4. You will come to know what is S2, what is S3 and what is S4. It is calculated here. Simplify, you will get S plus 1. The same manner, for any value of n, we can find the normalized transfer function Hn of s. Here I will show the table, okay, up to n is equal to 5 I am showing in exam. Maximum they will give up to n is equal to 6. So I will show here n is equal to 5. So when n is equal to 5, so you will get the what is the normalized transfer function for whatever with the frequency specification. You will get the normalized transfer function as shown in the table here. When n is equal to 1, you will get normalized transfer function as s plus 1. When n is equal to 2, normalized transfer function as s square plus root 2 s plus 1. When n is equal to 3, you will get s square plus s plus 1 into s plus 1. And n is equal to 4, this is the transfer function, and n is equal to 5, this is the transfer function. So by okay, like this we can calculate the Butterworth polynomials. Once you substitute and once you find out h2 of s, hn of s, we can find out the analog to analog transformation and can find the actual transfer function, okay, of the Butterworth filter. With this, I will conclude my today's class. Thank you.